This is part 2 of chapter number 15, Structure of Atoms and Nuclei. In first part, we have studied about the atomic model suggested by Sir J.J. Thomson and then the atomic model suggested by Ernest Rutherford. We have also seen that the Ernest Rutherford got the idea of atomic model, or he took the idea of atomic model from the model of the universe, that is sun is at the center and other planets are revolving around it. Now let us study about atomic spectra. Students, you know that when metallic object is heated, it emits radiations of different wavelength. Say like when the iron is heated up to a certain temperature, then iron becomes red hot and it emits the radiation. When these radiations are passed through a prism, you will get a continuous spectrum. So you can observe in the diagram how the continuous spectra is. So in the first diagram, the continuous spectra is given, and this is the spectra which you can observe by hitting the metals. Now, when hydrogen gas is which is inside the glass tube is heated or is given with a high temperature, it also emits radiations of certain wavelength. And when these radiations are passed through a prism, the spectra is observed, and the spectra is called as emission spectra. And in the first diagram you can observe the emission spectra of hydrogen. This is the spectra of hydrogen in a visible range. This is visible range. It means we can see these such a lines because this is a visible range by our we can see by our eyes, because we cannot see ultraviolet and infrared, as you know. So this in the visible range, such a lines of definite frequency or wavelength are observed. Now so these wavelengths are specific wavelength, say 410, 43, 486 and 656 nanometer. And as I said, this falls in a visible region. When these wavelengths are allowed to pass through the prism, the lines are observed, and these lines are called as emissions lines. This we have observed in the previous slide. It also emits radiation of specific wavelength in ultraviolet, infrared and the more region which has longer wavelengths. These spectral lines you can divide into the different series according to their wavelength or their frequencies, and these series are given with the name of different scientists who studied those series. For example, the visible series which we observe in the atomic spectra of hydrogen, this was given by the scientist Balmer. And there was a very different series. So the different series are, the first series which is having the lowest wavelength is Lyman series, then Balmer series, Paschen series, Brackett series and Fun series. So these are the series which falls in different region. For example, Balmer series falls in visible range, ultraviolet falls in Paschen series, and so on. Each series has a separation between successive lines decrease as we go towards shorter wavelength and then reach the limiting value. So from the shorter wavelength up to the limiting value, that is the max value of the series. So you can move from the lowest wavelength up to the shortest wavelength, so up to the longest wavelength. Okay. When Balmer, he played with the different numbers such as 410, 434, 486 and so on. He played mathematically with this number and then he gave an equation. The equation was like this: 1 upon lambda is equals to r into bracket 1 upon n square minus 1 upon m square. The observed wavelength of emission of lines are found to obey this relation. Now what is lambda, what is r, what is n and what is m? Where obviously lambda is the wavelength of a radiation, r is a constant. This is called as Rydberg's constant that we will study in the next topic. But remember, here r is a constant. M and n are integers such that n is equals to 1, 2, 3 respectively for Lyman, Balmer, Paschen, bracket and Fund series. Also, it is important that m is greater than n. Okay, that means m is the highest higher energy level than n. The wavelength decreases with decrease in m. As we move away from the nucleus, the wavelength decreases, and hence the wavelength decreases as the value of m increases. The successive lines in a given series come closer and closer to closer and ultimately reach the value of lambda is equals to n square upon r in the limit m is equals to infinite for different values of n. Now what is this? Students, if you want to find out the series limit or the maximum wavelength, then for that you have to substitute the value of m as infinity. And you know that 1 upon infinity is equals to 0. So our equation of 1 upon lambda, it reduces to r upon n square. Or you can say that lambda is equals to n square upon r. Remember this equation. When we want to find out the series limit, we are going to use this equation. And you know that here n is a principal quantum number which is equals to 1, 2, 3 and 4. Again I am repeating, for Lyman series n is equals to 1, for Balmer series n is equals to 2, for Paschen series n is equals to 3, for bracket series n is equal to 4 and for Fund series n is equals to 5. So you can find out the limit or series limit of any of the these 5 series by substituting the value of n and the Rydberg's constant r by using the given equation. Lambda is equals to n square upon r square. So remember this is important because we are going to solve examples based on these formulas. Okay. Now one thing, important thing you can say, atom of an element emit line spectrum. The wavelength of the lines emitted by each element are unique. Hence, the element can be identified from the wavelengths of a spectral lines that it emits. So you can say that this emission spectra is a characteristics of that particular element. Hence, atomic spectrum is used to be a signature of element. As every person has its own signature, you can say that every element has its own atomic spectra. Here the atomic spectra which we have observed in the first slide was the atomic spectra of hydrogen, but every element has different atomic spectra with different wavelength, and hence this atomic spectra is the signature of the element. So this is quite interesting to study the atomic spectra of different elements. Now let us move further. This is the hydrogen spectra. We will again come back to this hydrogen spectra after 2-3 derivations. Now the next important topic is Bohr's atomic model. We have seen what is the atomic model suggested by Rutherford, but there are some drawbacks or some difficulties or deficiencies in Rutherford model that was overcome or that was well explained by Bohr. So Niels Bohr, he modified Rutherford's model by applying the idea of quantum physics. He realized that whatever the model suggested by the Rutherford is correct. But to remove the flaws, he took the help of quantum physics. And what is important to explain the stability of a atom, and of course the stability of electrons which are revolving in a different orbits. So Niels Bohr, he took the help of quantum physics and the theory, Maxwell theory, and he gave 3 postulates, and by using the 3 postulates one can explain very well why electrons do not emit radiations when they are moving in a different orbits, or why electrons do not fall in the nucleus, as the motion of an electron is an accelerated motion. Hello. So let us study the Bohr atomic model. The first postulate, there are 3 postulates. So first postulate is the electrons revolve around the nucleus in circular orbit. This I have stated before also. And whenever the object is moving in a circular orbit, it needs centripetal force. The necessary centripetal force to revolve electron in a circular orbit is provided by electrostatic force of attraction between the electron and nucleus. This is first postulate, that centripetal force is provided by electrostatic force of attraction between electrons and nucleus. And you know that this electrostatic force is explained by or given by Coulomb. Yes, the Coulomb's law states that the force of attraction between force of attraction or repulsion between 2 charges is directly proportional to the product of the charges, product of the magnitude of charges, and inversely proportional to square of distance between them. So by using that, one can find out what are the electrostatic force active on this. So second postulates, radius of orbit of electron can only take certain fixed values, such as the angular momentum of electron in these orbits is integral multiple of h upon 2 pi. Or in other words, we can say that electrons revolve only in those orbits whose angular momentum is integral multiple of h upon 2 pi. Integral multiple means n times h upon 2 pi. Here h is a Planck's constant. Third postulate, an electron can make transition from one of its orbit to the another orbit having lower energy. Means electron can jump from the higher energy level to the lower energy level, and while doing so they only emit the electron in the form of photon, or in doing so it emits a photon energy, and that energy is equal to the difference in the energy, two energy levels. Let me explain it clearly. Electron will only emit the energy when they jump from higher energy level to lower energy level. And how much energy is emitted? The difference is equals to the difference between two energy levels. Okay, so this is Bohr's third postulate. These three postulates are important, so remember this. First postulate, the necessary centripetal force is provided by electrostatic force. Electrons revolve only in those orbits whose angular momentum is equal to integral multiple of h upon 2 pi. And third postulate, electron emit only energy only when they jump from higher energy level to lower energy level, and the difference between the two energy level is equal to the energy emitted by the electron. So let us study the Bohr's postulate in detail by using the equations. The centripetal force required for circular motion is provided by electrostatic force. So what is the formula for centripetal force? The formula for centripetal force is mv square upon r. This formula we have studied in our first chapter. And electrostatic force, as I explained, it is given by coulombs. So electrostatic force is equals to 1 upon 4 pi epsilon 0 E square upon R square. Okay, why E square? The two charges are E, and that's why it is E square. So this is Bohr's first postulate, that MEVN square upon Rn is equals to 1 upon 4 pi epsilon 0 E square upon Rn square. Here Rn is the radius of the nth orbit and Vs is the velocity of that nth orbit. Vn is the velocity of that nth orbit. According to second postulate, angular momentum is integral multiple of h upon 2 pi. So angular momentum, it is equals to I omega. If you substitute the value of I and omega, then you will get angular momentum as mrv. You can calculate it or you can find it out. How angular momentum, L is equals to mrv, because whatever the formula we have studied is I omega. So I is a moment of inertia which is equal to mr square, and omega is equals to v upon r. So by using that formula you will get angular momentum as mrv. Here the angular momentum of an electron which is revolving in the nth orbit is me rn into vn, and this is equals to nh upon 2 pi. And this is the stable orbit, where and when in this such a stable orbit electrons are revolving, they do not emit any radiations. Then according to Bohr's third postulates, electrons emit energy only when they jump from higher energy level to lower energy level. Here Em is the higher energy level and En is the lower energy level. So when electrons jump from higher energy level to a lower energy level, they emit a photon energy, and you know that photon energy is given by the formula h nu. Here again h is the Planck's constant. So these are the Bohr's three postulates. This is the pictorial diagram of Bohr's three postulates. In first diagram, the electron is revolving around the nucleus, and the necessary centripetal force to revolve electron around the nucleus is given by electrostatic force of attraction. In second postulate, we have studied that electrons, they do not revolve in any orbit. They revolve in only those orbits whose angular momentum is integral multiple of h upon 2 pi. And Bohr's third postulate, you can observe in the diagram, electron only emit the energy when it jump from higher energy level to lower energy level, and the difference is equals to h nu.